Good afternoon. I said about 20 people would attend. You're a bit more. That's good, because the title, first I heard somebody saying that it's too long, but I didn't create it, so somebody else pushed it in a bit, so my excuse for that. I'm a bit of a special case, probably, so I often depict myself as this. I'm a veterinarian by heart, so I did a veterinary degree, or I have a veterinary degree, and that's what I normally do. But I also hold, right now I'm finishing a master's in data science as well, so I'm a bit of a two sides, and people always laugh at it. I see people taking already some pictures of it. Mention it, yeah? Mention it on Twitter, whatever, I like that, so that's good. Why do I show this? I'm a bit of a data scientist with a focus on dairy animals, and I always promise people to show something about the industry, so you have a bit of an idea why I'm talking about this, because there's a reason why we are talking about this. So the dairy industry, very simple. I'll show this one. This is a graph from in the 50s. This is the graph that caused all of you to stop drinking milk because you thought you would fall dead because of the milk fat. So this was a graph, and people said that at a certain moment, if you have more fat calories coming from milk, you would die, yeah? And then you see that line or that fit. Problem is that the guy who initially created the graph forgot to put these dots, yeah, the real data, which eventually showed that there's absolutely no link between the, let's say, the fat intake from dairy products and the case you would die from stroke disease and so on. First bit of data science. The fact, of course, is this is already mentioned this morning about energy, but I have the same problem. Yeah, who will feed the world? Yeah, that's what I'm working in. Who will feed the world, the expanding world, which is very, let's say, the numbers are really high. We will need to feed these people. There's a lot of environmental pressure on the whole agricultural side of things. Yeah, but one of the things that I would like to show you, if this evening you have the opportunity to eat steak in Dublin, do it. The good thing is that you to produce the same pound of beef, that we have about 20% less carbon footprint than in the early 50s. For milk, it's even more dramatic. So each time you drink milk, you can now say, look, I'm this more efficient per gallon of milk or whatever. So this is the core, in fact, of what we're doing. There's the environmental pressure. Everybody thinks that cows will ruin the world because of our environmental footprint, which comes from the land use, which is the CO2, and then the methane from directly. So we have the methane from the animals. That's true, but we're all doing, let's say, we're trying to make this better. Efficiency is our, let's say, main driver of things. What are we doing, or what's happening in reality? It's good for you to also know, is if you drink a glass of milk, and then I promise you to go to Spark. If you drink a glass of milk, you can also choose for the others. Yeah? I advise you not to. Why? Very simple. The vitamins and minerals in your glass of milk are all natural. If you drink soy milk, it's not natural, it's added. And on top, there's a cost to it. If you look, the cost for a gallon of milk is still lowest given nutritional value. So if you go home, drink milk again. This is what I like to see. Yeah? Kids grow on milk. I have a 1-year-old boy from next week. He'll drink milk, not soy. Good. Efficiency is driving everything. So to give you an idea, this is an animal which now holds the record, and she's one of the record holders because she has the largest output in milk, yeah, compared to her ancestors. That's enormous. So this animal produces 95 kilograms of milk a day. Yeah, that's enormous. Eh? What's happening is that her input to output ratio, you feed her, and the output is bigger, so she becomes more efficient. And so what we in the business do is we look at this, yeah, via tools which allow us to get insight in that efficiency. So this is a graph of one of my PhD students, and it nicely shows what's going on. It's unbelievable how popular our business is because of all these possibilities. I have people producing Arduino, Raspberry-style sensors. You put them on the animals, and you can do stuff with it. Very recent, this is one of the people also, which is quite known in Ireland. So the current head of agriculture for Europe is an Irishman, and very simply, some weeks ago, he gave a talk. Everything in the agricultural business will move extremely, especially in Europe and North America, towards the data-driven decisions. Everything is data-driven decisions. To give you a bit of a flavor why or how this all fits to where I'm working, I work in a very large project which is called G+E. It's a European project in which we actually use data from animals to do prediction modeling, to look at efficiency in very different ways. Yeah. If you want to visit the website, you'll find it, or you can ask us if you want some more information. And I'd like to give you a bit of a flavor of how people look at it. So if you, for example, would talk to our project leader, he would tell you, it's a 9 million euro project, yeah, with different work packages. So there are different work packages. These work packages, they flow towards the end with a large dissemination work package that will help the entire agricultural world. If you talk to the animal scientists, they will tell you, for example, we have 5 different research stations. We have animals enrolled in these farms. These animals produce a detailed level of information. All these animals also have a kind of a predictor that's there, and we're going to analyze it. If you ask me, as a data scientist, this comes very close to what you probably understand better. What we will do is we will test and train models based on information we know from the animals, trying to predict their efficiency. Efficiency in very simply output, but also their greenhouse efficiency. That kind of things, that's what we want to do. So test trains based on a smaller number of animals. That's our problem. We need 100 million euros if we want to do this on a larger number of animals. But you don't like it, because you people, you think that we're destroying the animals. So that's always the balance that we need to find. Because of course we have a lot of columns and a limited number of rows. That's our challenge. So what's happening further on, and that's the nice part, we're going to bring the industry towards these models and validate, do our prediction models work? We do a genome-wide association study, so you feel me coming towards what the challenge will be, and then how do we use those prediction models in real time? We have a model, somebody trained it, maybe he did it in R, but how do you make it production ready? Nobody thought about that. No animal scientist thinks about that right now. So that's really the challenge of how do we deal with all those things. How do we host and maintain prediction models for the industry? The single most important question that the industry asks me is, Mil, what is the promise that after that project we will be able to continue with those models? And how do we do that? So that whole challenge is more than having some animals prediction models, and that it's the entire ecosystem around that. I will give you a bit of a flavor of what the data looks like in this case. Probably you noticed this one. So I've written small, big, and big, small. Why? I don't have big data. I have a lot of messy data. But for me, that's also data. Big data because of that variety. So volume in my case is there, but I don't care about the volume. I care about all the others. That's more work. It's especially the variety that gives me headaches every day. So to give you a bit of an idea, so this paper will be published very soon in a book about how to look at welfare and data, for example. Maybe it would be nice if we were able to show, look, this is the data set from a farm, and this is their welfare score from that data. That's the idea that could come. So what data are we talking about? I will show you a small video. This is, for example, one of the farms that is in our trial. So this is a robot, and you will see an animal. You see her nose already, I guess. Oh, no. She will be entering the robot. You see this is an animal entering the robot. So at a certain moment, an RFID tag activates the robot arm, and at that moment, that animal is milked. So that animal now, her udder is cleaned, so that you would not have dirt in the milk, because you don't like us to have dirt in the milk. But what happens as well is after this, and I think I can speed up the video a bit towards the position where I want it to be. Yeah. So at a certain moment now you will see that the process of cleaning ends, and these are, let's say, the cups with which the milk comes out of the animal. So at a certain moment there's an infrared camera over here. He will recognize the position of these teats and put the cup on top of it. You will see it happening now. You will see that it starts scanning, yeah, and then it will put on the first cup. This is how advanced things already are in the dairy industry. But maybe you think, oh, that's not advanced enough, because what's happening also is inside of this line, there's even people working on sensors that would be able to collect features from that milk, which are able to tell us something. This animal is sick, this animal does this animal is that. So people try to find, let's say, the phenotypes. For example, how much milk does he produce? And we try to find out, can we measure something in that milk that would be able to then help us predict things in advance. So, for example, we have the phenotypes, which you would call labeled data. Sometimes it's classified. It's our classes, but typically for us, for example, we measure glucose in animals, calcium, really insulin. Don't think that insulin resistance is something uniquely to humans. It's also there for animals. So, but this is the kind of data that comes in from the one side, and then we have the biomarkers. So what these people try to do is they try to find out if we milk the animals, can we use some kind of biomarker, which is typically a spectrum, for example, or a glycan profile, which is a kind of sugar profile. Can we use that to, for example, predict this one is sick? Because that would allow us to be much more reactive and have less animals become sick, or have them, let's say, give us a bit of a flavor of what's going on that herd. So this is this is typically the case for our industry and this project. So what we've done, for example, and this is an idea. So these are the animals in the different countries that we collected very detailed phenotypes on. So a lot of information on these animals, and then a lot of dimensions, observation, and individual records. We have intakes. I won't bother you with the details, but I think you start feeling the flavor of what's going on with all these different kind of flows of information that come to you. Then on top, we have a lot of different sources of management software on the farms. Then there is some cloud-based platforms where some part of the data is. You feel the difficulty coming. On top, and this is getting very interested, if you were in the session, I think 1 hour ago, there's not only humans, but also animals that we are genotyping. So what do? This is a calf, and when she's born, they put a number in her ear, so we recognize her. What we do right now is, if you see here, this is not a pinch anymore, but a hole. And the part of the ear is used to immediately being sent to a lab. And that lab, for about, right now it's about $20. For about $20, they will do at this moment, I think, 50K genome test on that animal. There are estimates that in, I think, 50% of humans will be genotyped. We will be there earlier on cows. Because the information is enormous, because we can think about trying to read also from the genome, this animal has a higher likelihood to become sick, yes or no. But how do you store all that data, share it? In the project, we have terabytes of information, and it's right now in the beginning what happened is people were sending the terabytes via email, post, so mail services. This is an incredible world, yeah? So there's a lot of RNA and DNA sequencing going on. To give you an idea, you need right now about 1 gigabyte of DNA per 1,000 animals, but this is interesting. There's a lot. One of the work packages is focusing not only on DNA, but RNA. Won't go into the details, but what you should know is that this produces about 10 gigabytes of RNA per animal, but we do it on different tissues. So we have uterine samples, we have samples from the udder, we have samples from the liver. So you see the data is growing enormously in a very quick amount, and people have, it's really difficult to have all the data, or let's say the animal scientists understand well enough to be able to productionize that let's say, chain. Hey, Emil, there's another update of the data. Very simply, an email saying there's a new update, but somebody forgot to add that one column, they did it afterwards. This is, in our trial, every week I get this kind of emails. So that causes me quite some headaches. Variety is extreme. Variety in data sources, in the dimensions, even in the people. In Europe, one of the biggest challenges for Horizon 2020 is people. It's not about data, it's about people. Trying to make people collaborate, communicate, the differences in budgets, and this one is also a messy one. Statistical programming. Most of the people that we're working in, or are working in the project are R fans, so they're completely turned to R. And then you have somebody like me saying, you should do Scala. So that gives tension. But that's the real world. Because in R, they will never be able to leverage the scalability, or on the scalability that, for example, a Spark will give you. So I'm trying then to learn them some Spark R, but that's not always that easy because they always refer, I need that package. So you see, quite difficult. Spoken languages, I've mentioned that. This is the reality. Who sees the issue? This is a Dutch cow. I never show Belgian cows like that, but who sees the issue? You see it? This one is number 65 and 66. So somebody just switched them, but this is reality. What do you do with unique identifiers? I stopped using unique identifiers. There's some nice packages right now in Spark where you can have a kind of fuzzy matching. Yeah? Instead of really saying this is unique animals, try to find out how likely are these animals the same based on features. Yeah? You have some packages, some of the ML libraries that enable you to do that. Veracity, issues with data that comes in. Something which is rarely reported. 20% of the animals in the world, in the US, are claimed to not have the father and mother that somebody has told us. Why? Because somebody was just not awake in the morning and he looked at in the calving pen and he sees two calves. There's a white one and a black one, and then there's a black cow and a white cow. So what does he say? This is mom from him and this is mom from that one. But in reality, it's much more difficult. But this is the truth, and this happens a lot. The moment that we see the whole, let's say, data bubble in 2009, we see issues we see people reporting issues in animal science, so data quality issues, and especially in disease. And this is what our project tries to focus on. How do we work with disease? Simple example again, these are some R plots from one of the guys who very simply notifies that the tails of what our residuals are completely off. And it illustrates that people just send data to us, they didn't check it, and then you find mistakes. Data quality issues is a very difficult thing when working with animal data, but people need to be aware. So my harsh reality, sometimes I'm in the barn, sometimes I'm doing this kind of thing. Data storage in the project, what do we do right now? Multiple sources of information. I have some web services that I connect as FTPs and CSV files which are sent to us. The question, this is all right now stored on HDFS, and then we collect it when needed. I have some services running automatically. But how do you document all those data schemes? How do you make sure that somebody else who wants to work with it? We've been playing with wiki-style documentation, Swagger-style documentation. Tony, who's also in the room and also already told me many times, use notebooks. Try to create almost your documentation in the notebooks, and that's true. So I started to do a lot of notebooks, for example, extract data from one of our partners, then you call the API and you get all the responses. That's automatically done. The nice thing is it's a combination of explanation, but also immediately doing. So instead of having the documentation and the doing separate, we combine it. So then the whole data manipulation, how do you share it? How do you make sure that everybody has always the right data? This is incredible. This is the number one difficulty in science. Secure it. A lot of scientists don't care, but how do you securely share data? How do you make sure that if there is suddenly animal information coming from in a lot of animals that it works. How do you make it reproducible? Notebooks. Probably some people will already agree with that. So I have very simple notebook for VP 3, 4, and 6. On 5, I'm not collaborating. That's a bit of a separate part. And people can dig in, and they see all my notebooks. They see everything what I've done. And that's what I like. The problem that we also have is that animal scientists, they like those wide formats. Yeah? The more features. One of the things that I do is in the data steps for the VP3 is I created to numeric long. So each of the features are instead of having that wide format parsed into a long format. I do bad coding. I'm a veterinarian, so don't blame me on the code. Just want to have sure that you have the principle. But then you get the following problem. You have those features inside, but then there's a lot of researchers, and then how do they interpret that one feature? How do they extract it? How do they aggregate some of them? And then I started thinking, okay, maybe I need to do it a bit different. So we have some of in the pipeline, there's a part of the whole dimensionality which is reduced, for example, on the spectra. I try to listen to all the, let's say, the people who really had the knowledge about the biomarkers. But then that's exactly the kind of case that I want. I do the documentation. This was an email from somebody sending me, Miel, this is the spectral data. You immediately document it inside of the notebook. This is the email saying, one of the guys, that I need to remove some of this. Otherwise, this would be lost. And then I do the rest of the PCA on top of it to reduce that dimensionality. But at least somebody else can understand why did I do it. And then the difficulty became is, for example, if you have this time series like from a metabolite, how do you extract that information? Animal scientists have typically been doing this with RAML, hierarchical models, random effects inside of that. That's one of the things that I miss, for example, in the whole Spark library. I've told it many people, that hierarchical structure, that's impossible to build right now. So, but what I started doing is, there are some nice publications also on weather forecasting, for example. Imagine that you look at all this data inside of a window until this moment. So all the observations over here, you can try to extract a lot of features. For example, what's the minimum maximum deviation? Yeah, what's the range? What kind of what's the average? So I tried to find a way in which almost all the different scientists, their ideas came together, and then you try to predict, for example, that post-observation average or maximum or minimum. You do the same, maybe, but for only a 7-day window. I'm saying, yeah. But these are the kind of approaches that you could do, or look at everything which happens to an animal in the days before something is happening and try to predict everything after. That's a technique that I liked because I could almost standardize it for anything that came into the data set. Because I wasn't going to do all the modeling one by one. I didn't want to do that. So window function, of course, this is the whole dimensionality curse which comes in because you blow up your features. Difficult, but that was one of the ways that at least I wanted to make sure that I wouldn't miss anything. So for those, this is going to be published soon, but this is a very nice function. So the window function, very simply, partition by animal, order them by time, and then take the range between the sliding window until now, for example, or the day before. So then you get something in the data frame. You can do something like take all the, for example, the count over that window. The nice thing is you can start playing quite intuitively with that function and make sure that you end up with a set of information that you can then model. This is a bit of a technicality. I did one thing as well, but I couldn't do it in Spark right now, and that's the RAML. I needed to make a flip and then come back. But then what happens is you get an enormous amount of information, and the nice thing is then you can build the loop on top of it, and then think about try to find all the phenotypes and the best set of biomarkers, so the features, and then push the predictive power and time for the analysis somewhere so you can analyze it. Because what I want to do eventually is find those models that are very interesting to look at. Because now what happened, all the animal scientists, one by one, were trying to check it. There's about 3,000 phenotypes. The chance that you miss one of them, which is interesting, is high. So eventually what we do is via random forest. It's not the best one. I needed to do a lot of tweaking to make this efficient, to make sure that it ran smoothly. Tony helped me for hours to try to find out where this got stuck in the beginning. And then it's pushed towards an elastic search and Kibana stack. Also, configuring that in a Jupyter notebook can be challenging, but eventually we found out how to do it. And then very simply, you do an import of that package and then save the result, and it's pushed into one of the indexes. And the nice part is, and maybe I think I can switch shortly, is once you are in the Elasticsearch Kibana stack, you can have people access that and show your data. So what we have over here is all the prediction powers ranked for phenotype 1, 2, 3, and this is the time for execution. So the average time, what you see is that it took about a minute for each of these models to run. This is, I think, data from about 1,400 models, but the nice part is that people can start digging in. So what are these models, for example? And on the fly, it will filter out those predictions. But on the other hand, people ask me which of the predictors, for example, or the biomarkers is nicest. I take out now, for example, this filter. This is a dry matter. This is a very interesting one for us. And what you will see is, for example, if you do it with glycan predictions, 6%, which is nothing, 66 and 0. So eventually what we were able to do is then select, for example, the milk metabolites as being better to focus on. I didn't say this is what we should do. I just tried to find ranking in the decisions, because that's what the scientists at a certain moment, they wanted. Try advice in which direction they would go. I like the Elasticsearch Kibana stack a lot because it's quite intuitive to do that. What's the future work? Create production APIs. Very simple. Those best models, the industry will feed in data and use those prediction models locally. But how do you do that? Yeah, how do you do that? That's the thing that bothers me. How do you make sure that that works? Validate those predictions, because yeah, you can have overfitting, of course. And then if I want to have more animal scientists work with me, I will have to have a way to implement common procedures into the ML package. BLUP, RAML, hierarchical models entirely missing at this moment, as far as I know. If you can help me out with that one, please be my guest. I'd like to acknowledge two people, especially our friend Shankar and Tony, for helping me out with the real Scala issues. And then, of course, the project, which is a large collaboration. And then these are, I have also, last year, some of you might have seen my talk from an industry perspective. So we have a project which uses this, but then with real animal data in a business-to-business. And quite some of the research was also funded a bit by Microsoft Azure, so I need to acknowledge that. And with that, I have 1 minute, 46 seconds. I would thank you very much, and I'll take any questions.
Thank you, Emil, for that very insightful, very incisive and illuminating talk. We only have about 1.5 minutes. If you have any questions, make it short. Walk up to the mic so we can actually capture your voice. Any questions for Professor Emil?
All the slides, by the way, you can find this presentation online if you want to see it again. You can find it on this website, and then on the conferences you will find everything.
Well, next time if you see a dairy cow crossing the road, pay some respect. So give a warm welcome to Niels Holsten from Ghent University. Thank you. Wonderful talk.